An exponential model says a quantity increases by 44% every 8 hours. We need the percent change in each 4-hour interval, while keeping the same growth factor over equal lengths of time.
The important structure is that 8 hours contains 2 equal 4-hour intervals. In an exponential model, equal time intervals use equal multipliers.
The choices are a 20% decrease, a 22% increase, a 20% increase, and a 44% increase. 22% looks tempting because it is half of 44.
That tempting choice treats percent changes as if they add directly, but repeated exponential growth compounds. Each new interval multiplies the quantity produced by the previous interval.
A 44% increase means the final amount is the original 100% plus another 44% of the original.
Write 144% as a decimal multiplier. The 8-hour growth factor is 1.44.
So if the quantity begins at an amount Q, then after 8 hours, the amount is 1.44 times Q.
Now let B be the growth factor for one 4-hour interval. Because the two 4-hour intervals are equal, the same factor B is applied twice.
After the first 4 hours, the model gives B times Q during the next 4 hours. It multiplies that entire amount by B again.
Multiplying B by B gives B squared. That two-step factor must equal the known 8-hour factor, 1.44.
To undo the square, take the square root. Since 1.2 times 1.2 is 1.44, the positive value of B is 1.2.
Algebraically, a squared equation can suggest a positive and a negative root. Here B is a growth factor for a positive quantity, so the meaningful factor is positive 1.2.
A factor of 1.2 means the new amount is 120% of the old amount.
Subtract the original 100%. The amount gains 20% during each 4-hour interval.
Let's verify the answer without relying only on the square root step. Suppose the starting quantity is 100 units.
After the first 4-hour interval, a 20% increase takes 100 units to 120 units.
The second 20% increase is based on the new 120 units, not the original 100. 20% of 120 is 24.
Adding that 24 gives 144 units after 8 hours. Compared with the starting 100, that is exactly a 44% increase.
Now I see why the two 20% increases do not add to only 40%. The second increase acts on a larger base, creating 4 extra percentage points.
Let's test the tempting 22% choice. Its 4-hour factor would be 1.22, applied twice.
1.22 times itself is 1.4884. That would mean a 48.84% increase over 8 hours, not 44%.
That calculation exposes the canonical trap. To split an exponential time interval, take the appropriate root of the growth factor. Do not divide the percent change by the number of intervals.
The source answer is choice C, a 20% increase. Its factor 1.2, used twice, produces the required 8-hour factor 1.44.
The reusable strategy is to convert the full percent change to a multiplier, count the equal shorter intervals, take the matching root, and then convert the shorter factor back to a percent change.
Here there are two equal intervals, so the shorter factor is the square root of 1.44. That is 1.2, which means a 20% increase.
2 consecutive 20% increases turn 100 into 144. The answer is choice C, a 20% increase during each 4-hour interval.